get started. So we have a couple of options for class today. So we could finish up any things on chapter 3, and then my thought is we could start on chapter 4. So just kind of looking ahead, next week we'll do chapter 4, and then after that is midterm. So if we start chapter 4 today, that gives us maybe next Thursday as kind of a review day. So I don't know how you feel about that. So want to start chapter 4 probably. So I did want to hit at least a few questions on the homework, just what I've seen from people turning stuff in. Oh man. Sorry, I just noticed my Wacom isn't mapped correctly. Oh, no, it is. That's weird. Okay. So some things that I saw. So gallium, what should this electron dot or Lewis dot structure look like? So one dot on the side, two on the top. So exactly. So it doesn't have to be two on the top, but right, we could move it around in any orientation. But this is what gallium should look like. So I saw some funky things. So same thing with beryllium. So that should just be two dots on one side. And then I think these were fairly straightforward. So of course with the ions, right, you just change them to the appropriate number of electrons now. So of course chlorine, if it has one negative charge, it started off neutrally at 7, add another electron, so now 8. Of course, it's satisfied in the octet. So I just wanted to re-emphasize, so what's the difference between polyatomics versus these monoatomics? Remember, polyatomics are some sort of charged molecule. So it itself is held together by covalent bonds, and then it has a charge. And then so if you're in class, make sure you get a polyatomic ion sheet handout for you. And then I linked to it already on Tuesday for everyone online, and I can link to it again. And so of course some examples. So the polyatomics, we could go crazy trying to come up with a bunch of polyatomic examples. So I'll just do sodium phosphate as one example. So phosphate, if you look at our chart, should have a -3 charge. So that's why I put 3 sodiums there to balance that. So versus a monoatomic, so that would just be, right, sodium chloride or something along those lines, where it's just one atom with a charge. So either a cation if it's positive, and anion if it's negative. And then, so this one, I'm not sure if we explicitly went over it, so I wanted to kind of retouch on this. And so, what's kind of interesting, and this goes kind of beyond what we've talked about, but going back, let's just look, if I can find it. So looking at what an ionic compound looks like, so we said, right, they're oppositely charged ions held together just by this crystal lattice, right? And so, again, there's no bond there. They're just held together by those forces. And then, so in water, what's going to happen is, let me start over. So water is a polar molecule. And so we'll get into this as we start chapter 4, but now this kind of gives you a taste. So we drew out the structure for water, it has this side over here. And notice that this oxygen has 2 lone pairs on it. So these lone pairs, each one is just 2 electrons. And so that means that this side of oxygen is pretty electronegative. In addition, this oxygen is extremely electronegative compared to hydrogen. So hydrogen, again, just has that 1 lone electron. And so you could draw an arrow too, like this. So this is just indicating where the electrons are being pulled towards. So all the electron density is being pulled towards this oxygen. So now I'll just rewrite it. And so this means that this side of water is essentially has a partial negative charge. So again, all the electron density is over here. And that leaves these hydrogens as a partial positive. And so right now we have a positive charge, a negative charge. So if we take our ionic compounds, they're going to be able to interact with water. So that's why water is polar, and then it can solubilize all these ionic compounds. And so in solution, the chlorine, again, if we're looking at sodium chloride, so the chlorine, since that has a negative charge, it would be attracted to the hydrogens, and then the sodiums would be more attracted to this negative end, so they'd be floating around in solution, again with the sodiums oriented more towards the oxygen, the negative anion, or in this case the chloride, oriented towards the hydrogen. And so this means that they can dissolve. So that's A gives us why they're soluble. But now it also asks, so why does it conduct electricity? Well, to conduct electricity, we need to have ions that can, of course, take our electricity and move it across. Because you are basically asking, well, how can we complete a circuit? So you have, right, your little circuit, light bulb. I apologize, I can't draw. And then you would have kind of 2 ends of your wire in a little beaker with salt. And so the reason it can conduct electricity is, again, it has these ions now, so that can transport our electrons, and then they're freely moving around, so they will make their way right from one end of our broken wire to the other, and thus completing the circuit. And so a light bulb would turn on. So that is why they conduct electricity. And then this last one, so why does table salt have a much higher melting point than table sugar? Again, I'm not sure it's really fair that this question was put in this chapter, but it goes back to, again, the structure. So ionic compounds are held together in this crystal lattice formation. And again, right, it can go on and on and on. So you could have like a big crystal, essentially. And so that crystal, it's hard to melt. So they have really strong forces between them. So with that crystal lattice structure. And so that's why these ionic compounds tend to have a very high melting point versus, so table sugar. Let's just pull out the structure of sugar. And so sugar is also a covalent compound, which is key. So then this is just the structure of sugar. And so I'm just pulling it up to show you what it looks like. But again, we haven't gotten there in the text. But this molecule of sugar, the only reason that it would be attracted to another molecule of sugar would be these intermolecular forces, which we'll go into what all that means. But basically, those intermolecular forces are a lot weaker than this entire crystal lattice structure force. And so you can see that just with like the relative melting points of covalent compounds versus ionic compounds. So covalent compounds tend to have lower melting points since you can break those intermolecular forces. So you would not be, destroying the molecule. You're not breaking bonds when you heat anything up. You're just separating these intermolecular forces, which would be better illustrated with water, for example. So water is pretty attracted to itself. Since again we have that oxygen. So they would be bonded here, right, these intermolecular forces. And water does have pretty high intermolecular forces of hydrogen bonding. So I'm just writing H bonding. And so this is one of the strongest. And so that's why, we consider water to have a high boiling point. So it has a boiling point of 100 degrees Celsius, which is pretty strange if you take into account its low molecular weight. But kind of the whole point is, right, still at 100 degrees Celsius, that's enough to break this, what we just finished saying was a strong intermolecular force versus, so sodium chloride, let's just look at the melting point. So sodium chloride's melting point is 801 degrees Celsius, and of course, right, water's melting point would be 0 degrees Celsius. Just trying to see, do they have a boiling point for sodium chloride? And apparently the boiling point, just so we can compare, is 1,465 degrees Celsius. So big difference, and again, it's all because of how tight they pack, and also you have the crystalline lattice forces, so that adds, right, additional stability. So you don't just have, two ions kind of being held together. It's the entire crystal lattice structure, and that has additional energy, and that's very favorable, and that's very stable when it's packed in that structure. So that is not as favorable to melt. And you can kind of see, right, if you were to try to just disrupt that, it would be really difficult because of how they are packed in versus any sort of covalent compound where it's much easier to break those intermolecular forces. All right, let's do some naming. Let's do the other way. So let's do these three. So sodium phosphide, sodium phosphite, and sodium phosphate. So come up with the molecular formulas. We'll go over them. I'm watching the chat too. And then actually, let's throw one more on there so we can say we did a variable oxidation state. So let's do nickel carbonate as well and see if we can write our formula. So what did we get for the first one? So sodium phosphide.
Na3P.
So here, Na3P, thumbs up. Sweet. I'm looking in the chat too. So good job on recognizing that phosphide, right? That's just referring to phosphorus. So that's another one of those that just tends to throw people off for whatever reason. All right, what about the next one? So sodium phosphite. So Na3PO3. So is that what everybody got? So thumbs up, excellent. So you looked at your chart. I see it in the chat too, excellent. So we found our phosphite, PO3 with our -3 charge. So good job with that one. And then the last one, so sodium phosphate. So Na3PO4. I see it in the chat too, excellent. So we all found our phosphate now with our -3 charge. And then we had 3 sodiums. And then what about this last one? So nickel 2 carbonate. Yeah, go for it.
NiCO3.
So NiCO3. So is that what everyone got? See some nods. So we can look at, I would start with just our carbonate. So we find it's a -2 oxidation state. And then our nickel is also 2+ here. So they're appropriate in that 1-to-1 ratio. Was there anything else that kind of looked tricky on the homework? Anything that I skipped on chapter 3 that we should talk about? Or any other questions before we start diving into chapter 4? So I see thumbs up in class. So don't hesitate to ask questions or stop me or anything, or we can always go back if things come up. So let's at least start looking at chapter 4. So chapter 4 is now covalent bonds. And so covalent bonds, this means that our electrons are now shared by atoms, and so these will be our bonding pairs. And so our bonding pairs, that's obviously how they bond together. And then we will also have electrons that are not shared by atoms, but maybe just hang out on one particular atom, and those are called our lone pairs. And so let's look at water again in kind of more detail. And so the first trick with making covalent compounds and trying to figure out how they piece together is you kind of have to ask yourself, well, how many electrons are coming to the party from everybody? So if we're looking at H2O, and again, this is a really simplistic example, but it will help you later. So how many valence electrons does oxygen have? So 6. How many does hydrogen have? So 1. So each one has 1, then there's 2 of them, so times 2. So this means, right, we have 8 electrons total to kind of play with. And then, so the other thing we want to ask ourselves is, well, how are they, going to bond together? So I have these 8 electrons to kind of pair them. But that's why I would go back to our Lewis dot structure. So we can draw, right, our Lewis dot structure of water. So we can already tell we have these 2 lone pairs. So these are probably not going to be involved in bonding. But then we have these 2 lone electrons, right? They probably want someone to bond with. And then we can, of course, draw our hydrogens out. So again, they just have one electron. And then so when you're kind of putting your structure together, you're just kind of looking at them and think, well, you know, kind of what makes sense? How can they fit together? And then the important thing is, do you, at the end, have the correct total number of electrons? And again, in this case, it's kind of simplistic. The other thing you can start off with doing is just draw, right, a single bond to each one. And we probably want to pick oxygen as the central atom here, since it has, again, 2 spots for bonding. And so that's kind of another trend you'll notice. And so in this case, right, oxygen are group 6, so all these tend to form, you know, 2 bonds. And again, that makes sense because they have these 2 lone electrons. So now we drew our bonds, filled in our other electrons, so now we can count them all up. So 1, 2, 3, 4. And then each one of these lines represents 2 electrons, so 5, 6, 7, 8. So we have our total number of electrons we brought to the party. They're all accounted for. And then the next thing you want to do when you're looking at your structures is the octet rule satisfied? And so in this case with the covalent bond, since they're sharing these, oxygen, right, feels all of these electrons. And so we can say it has 1, 2, 3, 4, 5, 6, 7, 8 electrons. And so, right, 8 electrons satisfied by the octet rule. So oxygen's happy. And then hydrogen. So each one of them feels 2. So they have 2 electrons, 2 electrons. And of course, this is okay because we said that hydrogen can be satisfied by the duet rule. And so it's 1s orbital is all filled up. So let's take a closer look then at all the diatomics. And so now the diatomics are going to start to make sense as to why they are the diatomics. So we didn't just pick things at random. It's not at random why they are like that. So we start off with hydrogen, or H2. So right, we can draw each lone hydrogen. Obviously, they're not happy. But now we can draw a bond between them, so they each contributed 1 electron to that bond. And so now they're satisfied. So the same goes for fluorine, bromine, chlorine. So if we draw fluorine, 7 valence electrons plus another fluorine. So again, right now they would both be unhappy, not satisfied by the octet rule, and so they would just instead form a bond there. So this 1 lone electron in each one contributes to the bonding, and then each fluorine has 3 lone pairs now. So just make sure you draw those all out. And again, you can total up your number of electrons. So fluorine, each one of them contributed 7 valence electrons. And so let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that looks good. We have the right number of electrons. And then we can see, each fluorine is satisfied by the octet rule. So this fluorine feels these 8 electrons, so it's happy. This fluorine feels these 8 electrons, so it's happy as well. So what if we look at oxygen? We have oxygen, and 2 of them. We're trying to make O2. So how many bonds do you think might exist between these 2 oxygens then? So you're saying 2? So why do you say that?
Well, because they both need 2 electrons to be shared, and the electrons need to be grouped up in pairs, so they need one with oxygen upspin, one with downspin for both, right?
Yep, so that works out
So it needs to
exactly.
be a double bond.
Yep, so very good. So again, goes back to this group can form two bonds. So in this case, you have two oxygens. They'll go ahead and now make what's called a double bond. So this is just referred to as a single bond. And now a double bond just means that they are sharing, right, two pairs of electrons. And don't forget to put in your lone pairs. So each one of these oxygens has two lone pairs, and then they are sharing our double bond. So now we can see, right, oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons that it feels. Same with this one. And then double check we have the right total number. So 6 plus 6, so we should have 12 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that looks good. So let's look at the last, at least, diatomic that I want to look at. Trying to pick a color. So if we look at nitrogen, so what kind of bond do you think will exist then between our two nitrogens and our diatomic? So how many bonds would you expect them to share in a diatomic? Yeah, I like that 3 answer, right? So now we have that same scenario. So notice nitrogen, so it has one lone pair, so that's fine. But then we have these 3 lone electrons. And so anything, oops. Let me pull up the periodic table or copy one over. Just grab this. And so that means that these compounds, so anything in group 5, if they're no covalent compound, they tend to form 3 bonds. Now phosphorus is kind of funny, but we'll go there later. But if you see like nitrogen, for example, it should be bonded to 3 things. And so in this case with the diatomic, so we have our lone pair on each nitrogen. And then we can see this most easily probably with the total number of electrons. So we have 5 plus 5, so 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Make sure your octet rule is still satisfied. So yes, right, 1, 2, 3, 4, 5, 6, 7, 8. And same with this other nitrogen as well. And so kind of the next question is, well, how do we predict the type of bond, right? So we were just talking about ionic compounds. Now we're moving into covalent. So kind of what's the distinction? And we kind of mentioned at least some broad characteristics. So we had mentioned that ionic, so let's at least rephrase out the generalization. So we said ionic tended to be metal plus nonmetal, and covalent we're going to learn is nonmetal plus nonmetal. But part of how we can predict the bonds is by this difference in electronegativities. So we had mentioned the electronegativity trend. So notice fluorine, right, is your most electronegative, and so electronegativity increases as you go across and up. So that leaves fluorine as your most electronegative. Francium is your least. And so you have to have, a periodic table with your electronegativity values. But what you find, and again, this is just kind of a general rule. But if you have a small difference in electronegativity from like 0 to 0.4, this would be considered a covalent bond or nonpolar covalent bond. And when we say something is nonpolar, all this is saying is that electrons are shared equally. So AKA, right, there's no difference in electronegativity. And so a good example of that would be any of our diatomics. So if we took chlorine, obviously it'd be chlorine minus chlorine. That gives you electronegativity difference of 0. And so that would be, right, a purely nonpolar bond. And then if we look, so if we have a kind of intermediate difference in electronegativity, and this is, again, kind of rough, so from about 0.4 to 2, and you could always see exceptions in different cases, but generally this means that we have now a polar covalent bond. And so let's look at this example. If we look at HCl, so again, how you calculate your difference is we just need to get our two values. So if we look at our chart, so chlorine has an electronegativity value of 3.6. 3.16. And then hydrogen is 2.1 over here. And so now we can just take the difference. So let me pull out my calculator. So 3.16 minus 2.1. And so that gives us, right, a 1.06 difference. So it falls right in that intermediate range. And so again, all that means when we have a polar covalent molecule is that now we have some unevenness. So this is just like a graphical representation of the electron density. And so this would match kind of HCl if we wrote it like this. And so this large electron density means that all the electron density is localized on your negative charge. So in this case, right, our chlorine, so it would have a larger bubble there. And then hydrogen would have that partial positive. So it looks something like there. And again, right, the electronegativity is telling you that that atom, if it is more electronegative, it is pulling those electrons towards it. So that is why it would have, right, a large bubble indicating where your electron density is. And then so we continue on. And so what you find too is bonding, you know, is kind of a continuum. And there can even be like discrepancies over, is it covalent, is it ionic? So it kind of depends, and you may have to examine the solid state structure. But roughly what you find is past the electronegativity difference of 2, that means that you have a complete transfer of electrons like with an ionic bond. So if we look up sodium chloride just to do that example, so we had said chlorine was 3.16 from before. So if we look up sodium, it's 0.93. And so if we take this difference in electronegativity, so 3.16 minus 0.93, so that gives us, right, 2.23. And so now that is large enough to be considered an ionic bond. All right, so now let's look at those different types of bonds again. So we kind of went over this, but we'll reiterate. So again, if we have a single covalent bond, that's just our normal bond where two atoms are sharing one pair of electrons. And so that single bond, again, has 2 electrons in there. So we saw that with water. And then in our double bond or double covalent, now they're sharing 2 pairs of electrons, so we saw that with our oxygen. So other good examples of elements that can double bond are especially carbon. So carbon likes to double bond with oxygen a lot, and then carbon makes 4 bonds total, so it'd be attached to something else. Or maybe it's CO2. In that case, right, it has 2 bonds to each oxygen. Sulfur can do the same. So you could have CS2, for example, so carbon disulfide. Oops. And so sulfur is in the same group as oxygen, so we would expect them to bond similarly, and so that is indeed the case. So sulfur has 6 valence electrons, just like oxygen. So you can tell, right, it has 1, 2, 3, 4, 5, 6 from each sulfur, 1, 2, 3, 4, 5, 6, and then carbon has those 1, 2, 3, 4 electrons that it's contributing there. And then we said we also had a triple bond. And so now, again, it's sharing 6 electrons total between them, so 3 pairs of electrons. So just like we saw with nitrogen. So carbon can also triple bond with itself. Oxygen can kind of triple bond, but that's going to be more like a charged species. And same thing with sulfur, so I won't write out those examples. So I'm going to skip this section for now. So let's focus on naming, since we just got off of naming ionic compounds. So then let's look at how to name covalent compounds. And so this is a lot different from ionic compounds in that the formula for a molecular compound cannot be readily determined from its constituent elements, because many the same combination of elements may form with different molecular compounds and different formulas. So just one example of this is, right, nitrogen and oxygen. So you can't just say, right, nitrogen oxide, because that wouldn't tell you anything. So they can be in a 1-to-1 ratio, 1 to 2, 2 to 1, 2 to 3, 2 to 4, 2 to 5, right? All sorts of different combinations. So now we have to have a little bit different way of naming them. So again, we said these covalent compounds, or sometimes they also refer to them as molecular. So anytime you see molecular, just also think covalent. And so they're composed of 2 or more nonmetals. So write anything on kind of the right side of the periodic table. And then, so how to name them? So write the name of the element with the smallest group number first. And so if 2 elements lie in the same group, write the element with the greatest row number first. And then we'll use prefixes to indicate the number of atoms present. And so in this case, and again, this is different from ionic, is that you use a prefix to say how many of the first element you have, then another prefix to give you the second element, and then the ending would be in "ide" again. So if we look, let's go and name all these nitrogen compounds. So if we wanted to name NO, so if you just have one of the first element, you don't need to say like mono. So in this case, this would just be nitrogen and then monoxide. And so we have pretty similar prefixes. I think they should be the same as the one used in the hydrate. So mono, di, tri, tetra, penta, hexaheptaoctanonnadeca, and you could go on if you needed to. So what would be the second one then? NO2, how would you name that?
Nitrogen dioxide?
Yep, so nitrogen, and now that dioxide to show that there's two of them. So then try the next one. So N2O. So looking in the chat too. There are people in class. So I see it in the chat. So good. So now we have dinitrogen and then monoxide.
Wait, isn't nitrogen dioxide supposed to be nitrite? Or am I looking at that wrong?
Oh.
Nitrite?
Well, we're naming nitrogen first, so it'd be dinitrogen.
No, I meant for the first one. Or the second one, sorry. Nitrogen dioxide. Is that nitrite or? Never mind, sorry.
So are you talking about NO2 negative?
Yeah.
So these are not the same.
Okay, sorry.
So this is a polyatomic. So that is, right, nitrite.
Yeah.
But again, that's for polyatomic, so that's separate.
Sorry.
These are not charged.
Okay, thank you.
Are polyatomics only in reference to ionic bonds, or are we going to also see those in reference to covalent?
Not in terms of like naming a compound like that.
Okay.
But yeah, the polyatomic ions themselves are covalent compounds, so that's like the only way they may come back to haunt you is not in naming, but I would be like, what's the structure of like phosphate, for example, and you'd have to draw it all out.
Gotcha.
But yeah, you wouldn't have like nitrogen, phosphate or something. That would just be weird. And then so this next one, so N2O3, so how would you name it? Yep, so dinitrogen trioxide. So let's keep rolling. So now N2O4. So what would that be?
Dinitrogen tetraoxide?
So dinitrogen tetraoxide. Excellent. And then last one we'll do of this nitrogen oxygen family. So watching the chat too. So what would we get for this one? Yeah, go for it.
Dinitrogen pentaoxide?
Yep, so dinitrogen. I see it in the chat now, so dinitrogen pentoxide.
Pentoxide, not pentaoxide.
Yeah, admittedly, I can't like spell very well, so there's like some rules about dropping the vowels. So if you do minor spelling errors, like if you write pentoxide or
You get the question wrong and get no points, right?
no, definitely email me because that can happen in the Blackboard with the auto grading. Because I have a hard time spelling, so I don't expect you to like do the vowel thing correctly. So obviously I need to be able to tell kind of what it is. You can't totally butcher it. But if you mess up a vowel or something, that's fine. And if Blackboard marks it wrong, just let me know. I try to check with the quizzes as I go through them, but I don't always catch everything. Yeah, and I don't want to penalize anybody for little points like that. All right, so let's name these other ones. I think we're getting the hang of it, but take a minute or two. So just name these 3 examples here.
Can you go back to the screen with the prefix?
So let's try these out. So what do we get for A? Somebody else have an answer? Nobody shy?
The nitrogen, I don't know how you say triiodine.
Yeah, exactly. Or so triiodide, yeah. Okay, I can't even spell it. Nitrogen triiodide there. So don't forget to change that ending to "ide" at least. It should have 2 I's in it, I believe. What about B? Looking in the chat. Anybody else want to go for it?
Was it phosphorus? Is it detra? I don't remember what the 5 is. Penta.
Yeah, penta.
Chloride.
Exactly. So pentachloride. And then last one here. So P4S10. What would that one be?
Could you scroll up again?
Oh, yeah. So what'd you say? Tetraphosphorus?
Tetraphosphorus.
And then
Sulfur.
sul. Yeah. Excellent. Teamwork there.
When do you drop the vowel?
I think you always drop it if there's double vowels, but honestly I'd have to look at it again just to make sure. That's why I tell you guys not to worry about it since you can't spell. All right, so let's trek on a little bit more.
Oh, right, one more quick question, sorry. So can a metal react with a metal or no? Is that just not something that happens?
Like sodium and sodium, or why is it getting darker?
I don't.
Mood lighting.
That was weird.
Like, stupid example, cobalt and nickel or something like that are in the same group.
Yeah, so they wouldn't react probably like metal to metal, like unless you're making an alloy, which isn't the same.
Yeah.
But you could have a metal-metal bond, but then they'd probably be attached to other things. So it's not just like naked cobalt plus naked nickel.
Mm-hmm.
It would be some sort of complex.
As I notice, none of the, at least commonly listed ones in the metals are have a negative ion.
Yeah. Oh, coming back on? I think it did. We're back. All right, we got light again. All right, so let's look at kind of formula mass and molecular mass. So a couple of things, and what's nice about the periodic table is, so if you look at this little number here, so this, and we probably need to explain more where this number comes from. So this is just either our average atomic mass, which is either an AMU, or what's nice about the periodic table is this is the same thing as its molecular weight, which would be in grams per mole. So either this is 1 AMU if we're looking at one individual hydrogen, or if we're looking at a mole, then this is grams per mole. So that's something that's really helpful about a compound, or about the periodic table. Sorry. So I think now's a good time to kind of talk about this. So I want to point out, so let's just look, let's take bromine. Bromine's a better example. So if we look at bromine here, the other thing I want you to understand is where the heck this number like really comes from. So if we look at bromine, if you were to look up like the isotopes of bromine, you would find that there's no bromine that weighs 80. It doesn't exist. But what does exist is you have bromine 79 or bromine 81. And what's kind of unique about these two isotopes is that they're found in pretty much a 50-50 ratio, which is pretty cool. And, right, so I'm just going to round and say, okay, that's about 50% abundance, 50% abundance. And so, again, this weight here is the average atomic weight. So I think about this, if we could take each individual bromine, right, it steps on the scale, we record it, and then we do like 100 of them, average the mass, that's what we would get. And all of that is just due to the averaging of these two isotopes, right? So if you had a pile, or like a mole of bromines, right, 50% of them would be the isotope 78. The other 50% would be that 81. So when you get the mass, right, it's about half of that. And so how you get your average atomic mass on the periodic table, that would be equal to your percent abundance of one isotope. So if isotope 1 times its molecular weight or its mass of that isotope plus your other percent abundance times your other molecular weight, and of course you convert percentage to a decimal. But roughly for this example, that would equal to, right, 50% times 79 plus 50% times 81, and that gives you roughly 80, which is about the mass that's there. So that's what they do for all these, just add up all the isotopes. Yeah?
So does that mean these numbers can change, say, if we find out that at the center of the Earth or something, there's a large quantity of bromine 78 or something, or some different amount of, we find out that the abundances are different than we predicted or thought. Would that change the number, and has it changed in the past?
Yeah, I mean, I don't think that is a possibility in theory, but at this point, I think all these numbers are pretty set in stone.
I more meant, have they been changed? Have they changed?
I mean, I wouldn't know that historically. I mean, these things are set over time. I mean, usually too, that doesn't happen where there's just like a random spot of an abundant isotope. Like all our isotopes are existing and in certain ratios, and that's how we've gotten
Yeah.
to them. But then the other point that we were getting at is that it's really, at least relatively easy, to find a compound's molecular weight. So we just have to add up, right, all our components, and again, that either gives us the mass of an individual atom. So in this case, they've done it for water. So they are again looking at the molecular mass of one water in this case. So they did 2 times 1, and you might have slightly different numbers on the periodic table just depending on the accuracy. So hydrogen, they have 0.008. You'll find small discrepancies in rounding. And so 2, because there's 2 of them, plus 16, or 15.99 for oxygen. And so this gives you, right, a mass of 18 AMU if we're talking about one molecule. Or, since this also applies to a mole, we could say, right, 1 mole of water then has a molecular mass of 18 grams. So does that make sense? So it's super convenient like that. Trying to think. So I think it would be best if we save this next part, because what I want to go over next is just kind of the geometries, but that would be like a whole nother lecture. And so I know we would be ending like 20 minutes early, but is that okay with people? So we'll end early then, because I don't want to start in the middle of all this geometry and then have to stop. So we'll pick up on Tuesday then we'll go through kind of group 4, 5, 6, 7, and 8, kind of look at the geometries, look at the typical compounds, and then again we'll relate them back to just the few geometries that we have to know. But I think that sets us at a pretty good pace. And then we've kind of gone over these organic structures before, but we'll practice them some more next week. So I'll go ahead, we'll end lecture here for today, and then just let me know if there are any questions. I know we're kind of moving fast, but it just kind of depends what pace you're at. So hopefully everything's kind of making sense and coming together. But if it's not, ask questions, get help now, get help early before we keep moving on and you get confused about some basic thing that we should clarify. And so I'll hang around on stream in case there are any questions. But otherwise, have a good week. Oh, I forgot Earth Day event tomorrow. So come say hi. So come to Earth Day.
Yeah, celebrate the birthday.
Yeah, I don't know if it's a birthday, but it's definitely Earth Day. So 11 a.m. to 1 p.m. So again, it'll be just right outside between the HEC building and the Student Success Center. And if it's raining, we'll migrate inside, but there'll be pizza. We'll have GF options, I believe. We also have apples. Like a crap ton of apples were donated. So come get some food.
I love apples. Sorry, I love apples.
Do you really?
Yeah.
Y'all come get apples.
I can't eat them hardly, but I fucking love
The
apples.
homework too?
And then again, I'll hang around in case there are any questions, and then I can take your question if you had a question.
You have to ask the teacher about that? You got 50, right? Or do you not remember? Oh, no, you can go, I'm sorry.
So the midterm isn't next week, but the week after, I believe. Because next week is week 4, and I think the midterm's on week 5, if I remember. Yeah, we'll probably do it during Thursday, because we can start it during our recitation period, and that'll give you like 2.5 hours to do an exam, which You won't need 2.5 hours. Oh, sorry. You need this for the homework and
No,
stuff.
just, I couldn't find, place to submit the lab.
The lab's submitted through Gradescope, but I can also just take the paper copy.
Yeah.
Yeah, yeah, somebody's streaming it, so either you can tune in live, or, if you're not feeling well, you can watch it
theoretical, it would be,
later online.
so if you go for the 121st element, starting there, you get to the G block, which theoretically should hold 18
Yeah,
valence electrons if I'm looking at
Yeah,
it
just
correctly. If you have the previous
Email
ones,
me,
it's
and
actually
then I'm
50.
always available by Zoom too, so if you wanna meet,
I don't know,
chat,
that's
or
why I was
anything.
checking first.
Okay.
Oh, and then,
Yeah,
During your
this
time.
is the other certificate?
or just like anytime, because I'm pretty free like Monday, Wednesday,
Yeah,
and
that's what I
Friday.
thought that would be.
And so those are kind of like my office hour days
Maybe.
for y'all as well, or I can even do like nights and weekends, like I try to be really accommodating, so just email
I was
me.
just gonna say, I'll email you.
Yeah, that's what I just say, like set up a time with me, whatever works.
Well, thanks. And I'll
Yeah,
see you
good
next
luck with your
Tuesday.
procedure.
Two questions basically. So one, the main reason I was this, so it's 50, right? As it would be n to the power of 5, or to 5, to the power of 2 is 25, which would be times 2 is 50. I was thinking it was 2, so the second n layer and 2 electrons in that, as I was misreading it, like 2s2, etc. So that's why I was confused at first before I looked into it more. And then for radius, essentially these are inverse relationships where the smaller the radius, the higher the energy, the ionization energy. Shorter the radius, smaller the radius, or larger the radius, lower the ionization energy.
Yeah,
So helium would have the most, or the highest ionization energy, right?
yeah,
And like, frickin' no, because that wouldn't be because technically it's like that. So it would be like francium would be the highest. Or
francium would be.
Francium would be the like largest, right?